meeting. So, hello everyone, again on Open Dais. So we are continuing our international scientific journey. So we started about 2 months ago in St. Petersburg, then we visited India, we were in Brazil, and now we are coming back to St. Petersburg to meet Aleksandr Penskoi from our home university, ITMO, who will have a talk today on software verification for ASIP CAD example. So Aleksandr, so let me pass the word to you. Let me stop share the cover slide so you will be able to share your presentation. So please, yeah, it's visible. So welcome to our stage, and what interesting do you have for today?
Hello. For today, I will speak about software verifications methods. I will focus on some non-traditional approaches which allow us to save our time when we try to verify complex software. And I give you some examples of how we make verification for our application-specific instruction set processors CAD. So the subtitle of this report is how to trust your team and yourself, because one of the biggest problems in software development is when we make some work and break our systems and don't know about that. And only customer can say it to us. First of all, I would like to introduce myself. I was graduated at ITMO University and at 2016 and as a PhD, and my research area is research and development architectural style for design multi-level embedded system. The main question is how to represent complex multi-level system, which process was organized on many levels of organization, at the hardware level, system programming level, machine instruction set levels, and high-level programming languages, and how to work with this computational process representation holistically. And that report is a result, is a continuous of that work and that research. Also, I have right now, I was an associated professor at ITMO University at software engineering and computer system faculty, and also associated professor at Hangzhou University at ITMO University. The main topics of my course is functional programming, history of programming languages, and computational process organization from general point of view. Also, I have some commercial engineering experience at Embedded System Design Center. I'm working on the system to measure energy in a small town, and I have experience as an architect on the system of manufacture scheduling software. And also, I was a founder of the project NITA, around which my speech was built. Our agenda. First of all, I shortly speak about quality in software system. I general overview that question, what is the quality? And whereas in quality control, quality assurance systems is the place of that speech, because I don't cover all questions or significant part of quality control questions. After that, I introduce my project, the ASIP CAD, and show you the key architectural decision of that project and show why it's so hard to verify correctness of that software. After that, I very little speak about our development processes, and after that, going to verification methods which we applied to that project. Before I continue, I need to say that that project uses a very specific technologies for development, and usually it's not a mainstream technologies, but mostly questions, most methods of verification about which I speak, you can use in different programming languages, including mainstream languages like Java, C, C#, and so on. Okay, let's continue. Quality of software systems. Before we start, we need to define what is the quality of software system. And here we have two opposite opinions on these questions. First of all, it is a traditional engineer concept, traditional engineering definition that quality is a conformance to requirements. That definition presented by Philip Crosby in his work Quality is Free, and it's not fully applicable for software engineering as a practice, as a discipline. What is the main consequence from the definition? The quality is conformance to requirements. First of all, that we can prevent quality degradation of our systems, and we have oblivious steps how to improve quality of our systems, and we can do it continuously. The second consequence is the performance standard for our development process should be a zero defects, which means that all properties of our system should be consistent with system requirements. And the last one, measurement of quality is the price of non-conformance. And when we make decisions about how to measure quality of our current systems, only what we need, it's a price how to measure properties from our requirements to prove that our system have huge quality. In software engineering, we have a different point of view of what is the quality, because the definition from Gerald Weinberg sounds quality is a value to some person. We cannot strictly define requirements to most of the systems, and the only way to do that is take the requirements engineering as a part of development process of our systems. And continuously, when we define our systems, we should define its properties, its requirements, and establish a continuously control system for the quality. And of course, if we not define the objective quality of the system, we can speak about that quality is only a personal view, personal opinion about quality of the system. And consequently, we have the result that when we speak about quality in software engineering, all of the time, we can speak about the trade-offs between different stakeholders. And for example, one of our software, but it helps only 1% of our case. What's happened? Ivan, anyone? Is it work? Chat. Plug it. Yeah, I can see the presentation. Okay, great. I hope you hear me and I can continue. So the trade-offs between different stakeholders usually means that if we pay extra attention to one stakeholders, we lose from another point of view, and that is a common problem. And usually we don't have ability to define what is the correct system definition, what is a full system requirements, and how to work with that. So we know that quality of software is not a well-defined concept, and we need to work with it in a special case, in a special situation. But we can define the four major, but not all of them, elements of quality software, because without any one of them, we cannot in practice provide the quality software as a result of our development of our job. First, it is a product vision. That means the common understanding of stakeholders and their needs, their requirements. Usually in software engineering, we have a separated specialist to work with that. Then he can call it as a product owner or a business analyst, and his main task is how to define system vision and define what it should do, what opportunity is addressed by that system, and what opportunity allows the system to be developed, to be created. The next essential element of quality of software, it is a project management, because any project is a composition of many processes which should integrate into the whole line of the project development. Interaction between different roles, different agents in our project should provide the quality software which is addressed to requirements, which is developed in an applicable budget and for fixed time. As some specialist says, nothing can be more bad for your project than the bad project management, because taking a wrong decision can ruin any another part of the project. Because if we have in our project the real problem, the real unexpected situation, the worst thing what we can do with that and continue working as we say Frederick Brooks, if we have for that project, but not allow to finish it in time. The third part of quality software, it is a routine of development processes, because if we make a very small and short project, we don't really need to pay attention to the processes. But if we make system with many peoples and for a long term, we need to establish development processes which should automate, organize, regulate the development processes, because without that, it is impossible to set the end point of development process, to find the such point in the time when all part of our system, all development activities was connected into the full solutions. And the last one is acceptance tests. It's an end user testing, which bring our developed system onto utilization stage, when the system provide benefits to its customers and make reason to pay developer for that systems. In this report, I will focus only on routine development processes, and all another questions is beyond the scope. And next slide. The pictures on the right side you should see many times, and it's not original, because the classical term is that we have three properties of any system. It's a low cost, fast developing, and high quality, and we can select only two of them. But in practice, especially for software engineering and software development, we can ask a very bad questions. The bad question sounds like, can we actually develop high quality systems if we have infinite time and infinite budget? And in practice, usually we can not to say yes to these questions. Also, I need to note that in many projects, depends on its on business in which it's developed. We can set two questions. First, the business needs usually have a high priority over the quality. Why it happens? Because time and budget for business usually it's a showstopper, because without budgets and without time we can not make work done. We cannot start the work. But the quality, it's a more complicated concept, because how to measure it for system underdeveloped, it's a very hard questions. And in practice, we don't have ability to measure it with correctness, especially for software system when we cannot define all system requirements at the project start. When we need to make assumption, when we need to explore our external dependencies, when we need to explore our user needs. But in practices, when project is end, we can be catched in a bad business say a lot of money to that project, so we should continue. But usually in this place, business don't work on quality control systems and project quality control. They focus only on the speech estimate of how many time need, and continue work in the style which was beyond the continue of the work. And as a result, we have a project which cannot be done, but only can be killed by the management. So in this report, we don't focus on quality at all, but we focus on a little bit narrow questions about how to prove properties of the system, essential properties of the systems, which is make it executable, workable, applicable, but don't speak about the production properties of the system, product properties. And the second step of narrowing report scope, that we will speak, quality control has two processes, two key processes. The validation processes, when we need to check, is our system satisfied to stakeholder needs, to our customer needs. And the verification process, when we need to check compliance between formalized requirements and the software. And we don't focus on validation because it is a very complex problem which cannot be checked without context of specific problem. And usually it's not a computer science or computer engineering problem. It's a business problem. But verification, it is a question about how to check our product, our software to compliance with the formalized requirements. And we can separate verification methods into two groups. The static verification, in which we don't need to execute software, but see on it as a specification and can prove formally some properties, usually some general properties of the system. For example, all programming languages check program or if it is a static typed programming languages on interaction between software components. And the dynamic verification. Usually that means that we can execute our software and check their behavioral on a specific data set and check the result of it. And that can prove that system work in these specific cases with this specific data. But it is very hard to make consequences of general properties of the systems. And all software engineer in practice see many of them. Okay. Project specific. I need to speak about context of the project. First of all, it is an ongoing project. So all what I say is under development. Some of the parts was fully implemented and used in development process routine at each commit and each push and each request in our project. But some part, some essential component of the system is not developed yet. So I mark them but dot lines. And second point, second item, right now, that is a closed source project. But in the middle of this year, at summer, it will be published on GitHub, and you can see all about I speak in practice in source code and try by yourself if you're interested. So what is the NITA project? First of all, it's a pet project. What does it mean? That means that it is a just for fun project, which is don't have any significant commercial outcome right now. And it is not priority. What does it mean? That means that we don't, in our project, have a strict deadline for developing something. And we can make decisions not based on commercial goals, commercial tasks, but also based on what question is more interesting for us as a development. We can switch technologies, we can make experiments with new approach of developments. We don't need to make fast solution of the problem. We always have a time to continue working on the project. That is a problem because such task, such approach usually tend to create infinite project. But in our case, we make a huge platform to make a commercial project in future when we're done with most essential and most critical part of our systems. Next, what is some examples of commercial project restrictions? The first question is where we can take our team, where we can find our developers. And the only way to do that, it usually that restrict us on only widespread technologies. Because if we use Java, we can easily find Java developers. The same for Python, for CDS, and so on. But here we select many not widely spread technology. The main programming languages for our software is Haskell. The main tools for FPGA development, it's Altera and Quartus, not Xilinx, and so on. And also, we have two problems as a pet project. We have non-regular contribution to that project because many of participants have their work and cannot spend a lot of time to the project. And as a consequence, we cannot say the deadline and say when we actually deploy our system as a final solution, as a final product. Also, it is not only a pet project, it is a research and university project, which means the main goals for the project right now, it is articles, conference participations, and protection of bachelor, master, and PhD students. So from this point of view, it's very native goals for pet project, because we can continue work, we can make a small steps in our project, and that is a result which allow us to continue our work. The next properties, we can pay extra attention to a narrow question of our system. For example, on the verification problem, because when we need to develop a specific system, we can make fast solution for some technical problems. But here we can focus on the problem and find the general solution for it, because it may be not necessary for the system as a project, as a product, but very necessary to write PhD thesis or master thesis as we need. The second, we have open requirement list at present, because right now we don't have a specific application with specific requirements. We can be free in our decisions. But that's also a problem for the project, because it's very hard to focus it on the question. And one of the focus for today for the project is developing accelerator for system dynamics. But I return to this question a little bit later. And the last one, the team mostly consists of the students. And as a result, they are not a professional right now. When they onboarding on the project, we need to teach them about many questions about the technologies, development processes, and so on. So it requires a lot of babysitting for their work and a lot of mentoring how to do things right. So that requires to pay extra attention to development processes, to automatization, how to perform the project from this point of view, because that, for some of them, that is the first big project to work. And the last point is when you work with students, they usually have a huge problem with motivation, because if it is a big project with hard learning curve, you cannot, you need to perform fast feedback loop on their work, because if they start to work on the systems and spend a lot of time to make a very simple task, their motivation can decrease. But if you can organize the fast feedback loop by automatic quality control systems and development process, it can increase motivation and put them deeply in the project. What is NITA project from the product point of view? What is the system and what task it can perform? NITA project is a project about developing the CAD for generation and programming hard real-time application-specific processors. What does it mean? Usually, when we need to resolve some computational task, we have three options. First, we can use general purpose processors and simple program our software and execute them. What is disadvantages of that approach? It's a high energy consumptions, not very high performance, and not real-time execution. By real-time execution, I mean that we can define with high accuracy how much time algorithm require to execution. It is necessary for many controlled systems when we need to control over the physical processes and physical objects. So the second option is use the GPU. And for today, it is one of the widespread approach to develop a neural network or some algorithm with linear algebra. And GPU require a very special kind of algorithms to be executed, just because it it allows to execute algorithm concurrently on many cores, but at the same time that is restricted to single instruction stream and many data instruction streams. So in case if we need to develop system, some algorithm which not correctly mapped on GPU, we have options that to use FPGA. That is the approach which allow us to define digital scheme by software. So we don't need the manufacturer to produce our hardware, but we can form it on the FPGA chip, and that work as a real ASIC, as a real integral scheme. And that allow us to create the custom software, custom hardware for our task. And usually that significantly improve performance and reduce energy consumption for our solutions. And the problem of usage of FPGA for the project, the main very specific skill set for the developers, because the normal software developers cannot design the hardware from the scratch. They need to educate how to do that, understand how digital schemes work, and only after that they can really write the software. For today, we have a different approach how to develop hardware by software developers. And usually it can separate it into two groups. It's a high-level synthesis, which allow us directly write software in, for example, C, and usually it is the C languages, and translate it into the hardware and use it. But usually it's not a normal C programming languages. It is a very special subset of C with additional pragmas to instruct tool how to synthesize the target hardware. And the another approach is application-specific processors or cross-grained reconfigurable array architecture, in which we can speak about what blocks form our processors, and after forming it, we can program it in a very efficient way. That allow us to develop some embedded control or cyber physical systems. It's widely spread as approach in hardware and software testing and rapid prototyping when we need to create very high speed, high performance, and high energy efficient solutions, and also for coprocessors and accelerations. What is the main features of NITA project of NITA CAD? That allow us to cyclic execution of algorithm, which provide high speed and high parallel execution, and can be. And for example, if we want to design accelerator for system dynamics, we can do it by additional processor unit for that task. And if we need to digital signal processing, we can add to our processors filters for resolve such task. And of course, that project provide high-level languages to programming the processors without deep knowledge about how hardware works and how computational process should be scheduled on it. Right now, it is a Lua programming languages, but we're working on XML support. Here on the screen, you can see the workflow of NITA project for the customer, for the users. And that start from the application algorithm descriptions and micro architecture. It is a program on the subset of Lua languages for right now. Usually it is a simple algorithm from control engineering or some toy examples of system dynamic models or mathematical. By microarchitecture, I mean the composition of process units and their interconnect, which allow to describe the processor should be organized, provided to CAD to be used for application algorithm. So our users define algorithm on the Lua programming languages, define microarchitecture from the process unit library, and if they want and have enough experience, they can add their own processor units and pass this information to synthesis method to the CAD itself. So the CAD hardly work on that and produce the project for external FPGA design software, which can generate a program, the FPGA with hardware and software part of NITA processors, and generate the controller software which can be executed on the system on a chip, which usually includes some processor. In our example, it's IRM processor and FPGA chip. They can interact and transfer data to each other. And right now we can go forward to the NITA project development stack and internal organization. And here I can define some problems of verification of that project. First of all, I need to speak about the major component of the systems. In the center, you can see the NITA CAD. That is a monolith of Haskell source code, which implement the synthesis method of the systems that transpire for any input programming languages like Lua, and the model of the target system, which allow us to schedule and generate target software and hardware of our processors. And here you can see the two connection points. First of all, it is a introspection user interface that allow us to analyze and work with CAD and analyze how it works, what decisions that make, and debug our solutions. Why it is necessary? It is a part mostly for instrumental and developer purpose and not for the target user, but we need to implement it to make our work done, because without such instruments, we cannot develop efficient synthesis method and efficient solution for our systems. And here we have the second technology in the project. It is a TypeScript and React framework, which allow us to develop user interface as a single web page application. Another connected box, it is a ML-based synthesis method, because make a decision about how target processor should work, it's a very complex task which involve many metrics, many variables, and so on. And we can do it by ourselves and define objective function for that. But in practice, it's a very hard task. So right now we work on the ML-based solution for that. And that introduced the third technologies in our project. It is a Python programming languages, which should be integrated with the main part of the system implemented in Python. Next technologies. When we work with hardware, we can not describe it in Haskell programming languages. We need to use special hardware description languages. And here it is a Verilog programming languages, hardware description languages, which allow us to describe how our hardware works in a very low-level way. When we don't think about hardware as algorithm, but we think about it as a digital stream with MOOCs, wires, registers, and so on. And here we have two very closely connected parts, because at the same time, we need to describe predefined hardware implementation of our processor units. We need to generate some part of the hardware on the fly when we make target systems. And also we need to plan computational process for that hardware in our Haskell source code and generate the software for that. And the last point is a controller. You can see it here, which means that we don't need only to make systems which generate hardware, software, and they should work together. But also we need to generate controller software to work with applicable environment with that. And here we have the last technologies, the Rust, and that part of project is under development and not started yet, but in a small time we will continue work with that. Okay, and here some key difficult of verification of NITA project. or project itself. The first two is its extreme learning curve of the subject, because to fully understanding the project, or for example, only one process unit, the participants should know the digital stream design, how it's work, should know Haskell programming languages, should understand how synthetic process work, should understand how hardware can work, should understand deeply understand NITA architecture, how it works on different level of operational process organization, at compile time, at scheduling, at the target system on utilization stage. And take all that question in once, it's a very hard time. So the question which move from understanding mostly to the development process routine is checking the consistency of all these parts of the systems. Just because it's a bad assumption that at the start, at the onboarding on the project, that junior development can understand the whole system at the same time. The second point, it's not well defined. It's hard learning curves for the tools, because that point written from the general software developer point of view. And from the general software developer point of view, the hardware work is very hard and Haskell programming languages is very hard. But because it is a pet and research project, it's maybe key questions to select that project to participate, because that allow team member to apply what he want, what he like in that project. The second difficulty, the third difficulty, it's the project have many strongly linked software components, because and you can see it, we have the hardware implementation of process unit and processor unit models, which is required to synthesize target software, and they should be consistent to each other, because if they are inconsistent, they cannot generate the correct target system which can work in practices. And many such connections lie down not inside one technologies, but across many parts of the systems. And here you can see by blue cycles some of them. Here you can see the integration problem, the gap between user interface and CAD implementation, because that require to make a bridge, make an interface across different technologies, which usually is a pain. Here, the main problem of that project, how to make consistent different part of the system. And the main problem is that in a normal project, usually on the hardware and on the software works different specialists, and how to establish their communication and how to continuously check consistency between different parts of the system is a very hard problem. And the problem, one of the part of the problem is very late integration, because if we make a error issue here on the hardware level, the real error inconsistency we can find only here when we produce the target system and run it in a real environment on the hardware or in a simulation environment. So I will speak mostly about these two cycles, just because this one and this one is not implemented yet, and it's only a future task for our project. But before I go deeply in technical details and verification methods, I will speak a little bit about our development process. And as you remember, the NITA project is a research pet project. So we use the following practices in our project. First of all, it's a weekly meeting, which allow us, and which can apply it to any commercial project because they have the same problem. First of all, it's a weekly meeting which allow us to dynamically manage the development process, set task, correct task, change the task, and which is a very important point, preventing sticking team member on the same task. It's the source of that problem is a high learning curve, and the normal, not normal, but the usual situation when some junior developer try to resolve some task and stuck on it for days, weeks, and maybe months. And because usually it is a student, they have another options and can switch to another project. So the weekly meeting allow us to fast recognize that case and correct the direction of each project management members. And of course, the general point of any meeting is experience exchange about the project and also about the technologies what we use in our project. The second practice is a code review on the GitHub by mentors and team member. We perform it not only for quality control on conceptual level, what task was done and how it was solved, but also for experience exchange between the member, because the best way to start writing the good source code, it is reading good source code and try to understand bad source code. Because when you have experience with working with not the best software, you immediately start to understand what is a good software, what is a good solution, good code style. And also we heavily use continuous integration because that is the only one way how we can continuously check quality, continuously verify project state, and mostly we'll speak about it at the last part of the report. First of all, it's auto format of source code because the culture of the software development require it, but in practice, especially for many junior development, don't allow to do that in manual way. And the only way is a heavy usage of automatization in project, also in case when we reduce some quality, abstract quality reasons. And zero warning suggestions, because that allow us to write more clean and more correct code, avoid some mistakes. It's a hard use of different lean tools, unit integration tests, and automatic documentation generation. I will not speak about the general tools, just because everyone who has practical experience already know it. They know what is integration test, what is a unit test, how to do it, and it's not a topic. But we will continue with some not widely spread verification methods, which allow us to resolve some problems a little bit better than by normal methods and normal approach. First of all, I call that test by interactive examples. What is the problem to solve by that methods? It is first project documentation, because when we try to document our software, two main issues what we have with that. First of all, the documentation can repeat the source code. So you can simply remove the documentation and you don't miss any information, just because the documentation should describe the only questions which cannot be directly described in software, in source code, and as part of it. If we can encode the meaning of function in its name, we should do it. The second, the documentation is very good when documentation provide to the developer the examples how to use it, how to use the component, how to use some function, and so on. And in this case, the documentation is something which is very similar to unit test, but that provides the problem that usually we have unit test in one file and its implementation, function implementation in another file. And the only way how developer can read it at open one file, read documentation, some general understanding on how some component work, after that jump to the test and see a lot of tests which mostly directed on checking component functionalities. But what's happened if we can write in our documentation some examples of the component usages and immediately check its result by automatically solution. It allows us to keep documentation up to date, because if we change our component, our software, we immediately see it on CI, that something going wrong. And also, when we work with examples, we can find it near the main documentation of the component, and that allows us to reduce time to searching information and use it. So the tools of that kind is usually called doc tests and widely spread in the Python programming languages. And the example you can see on the right side. And here, how it works usually. Usually it works that the tool find interactive examples in source code, evaluate it in a REPL, and compare the actual result is presented in the documentation. And if any difference can be found, the test was passed. And that approach is widely spread in many programming languages, and especially in languages with REPL. And if it is not, you can simply implement it by yourself if you need it. What is the main restriction of that approach? The main restriction is that objects for testing should be a little bit simple, because if you need a lot of steps to initialize input data, the examples cannot be a part of documentation, because if you open some component and usually see the very long read about how to work with that, you will skip it and try it yourself. But only the short example is really informative and applicable in practice. The next, I already say that one of the biggest problem of our project is a gap between different technologies and different part of the project. And one of the main reasons why the core of our CAD was implemented in Haskell, it is the static type systems, the powerful static type system, which allow us to check many invariants of our software automatically and for free. We don't need to pay a lot of work to check consistency, because if we do it in dynamic programming languages, we need to write a lot of tests to check the questions. We have two parts of our project. One part, it is written in static typed programming languages Haskell. Another part is a user interface which written in TypeScript programming language, also statically typed. How we can automatically check consistency of that two component by type system, not by our hand, by unit test and so on. And here we have at least two available options, which was rejected in our project. First of all, it is a manual implementation in accordance with IP specification. It's a classical development approach when we need, first of all, we need to define our API of the CAD, and after that we need to implement backend part and front-end part in accordance to that. But what is the problem of that approach? That correctness of specification and its implementation on both sides, we need to manually prove by test, by checking, by our development. And usually that approach need to write a lot of boilerplate code, which require a lot of time for development, but also don't bring any functions to our software. Usually it's a very boring source code which take one structure and regroup data and another. So we decline this approach because it's required too many hand and manual work. The next approach, use static typed language neutral mechanism for serialization data structure. And one of the most famous examples is Google protocol buffer and the Tectonic standard ASN1, which allow us to describe protocols on general in language independent form, and after that translate its specification to both technologies and both languages. What is the problem with this approach? Of course, it is a very good approach and allowed to develop many systems. And it's a reasonable approach when you need to implement many clients, many services to work with that data. Because, for example, Google protocol buffers have many backends for its implementation supported by Google, and any a little bit spreaded programming languages has own implementation for that. So, but that raises two main problems. First of all, we need to recreate the gap between the transport and application levels. Because usually when we implement API, we don't speak about the transfer data, only about transfer data. We only speak about API structure, about the life cycle of structure and so on. And the general approach for that today is a REST API. So when we use something like protocol buffer or ASN1, we need to know that gap between transport level, which is automatically implemented, and interaction level or application level of these protocols. And also we have some restriction for from serialization mechanism to implement our systems. So we decline it, not because that is a better approach to organize end-to-end static typing, just because we have better options for our project, and you can see it here. It is a server-driven code generation. When we develop systems with client-server architecture, sometimes we can say that we have the main part in server or main part in client. And for example, if you develop the simple application like another one to-do manager, you don't need to implement some complex backend. And you can design it in client-driven way. And usually that calls backend as a service. And that approach means that you define the patterns of access to the data on the server side. And based on this pattern, you can generate server-side software to work with that. So you can focus only on your client-side development and get the backend side, the server side as a services, as a auto-generated software. And it is a popular way to develop client-server application for mobile device when all your work was concentrated inside mobile phone. Another way, it's a server-driven development, server-driven code generation, when we can define our REST API, and after that we can automatically generate what data, what access method we have to that API, and what data can be sent and received by this API. Also, that approach allows us to use with multiple, to implement multiple clients, which is a common requirements, but not for our task, and generate auto IP documentation to the software. So we make our solution based on some library, some framework for develop REST server for Haskell programming languages and for marshalling data to the JSON. So we implement the following flow. You can see it here on the screen. We have many elements of implementation, and only few of them will be written manually, and they are statically checking the consistency to each other across different levels. We start from the native Haskell data types, which we use in our normal Haskell source code without any specific adaptation to it. The next level, it's some Haskell types may be infinite or redundant for the user interface and for the task. Because Haskell is lazy languages, it's a normal work with infinite type. But it is impossible to serialize it into JSON and transfer it to the user interface. So we need to create some utility Haskell data type to work with that in a correct way. And also, we need to implement that manually. And usually, it's not a very hard programming. It's a traditional boilerplate code for such application. What we take JSON have automatically JSON serialization functions. We automatically, based on native Haskell data type description and utility Haskell data type description, generate TypeScript types for our user interface. So if we change something in our CAD, we automatically receive these changes on the TypeScript level. And also, as consequence, we catch the compile time error, compile time type error in that case. So we achieve the checking consistency automatically. The next step, marshalling between Haskell and HTTP API implementation, because we need it to connect the endpoint of our REST API and our native normal Haskell function to work with that. And that connection, we only describe it. All marshalling in that processes will be automatically development for us. Also, we automatically generate API for service request functions in JavaScript at the same time when we're marshalling between Haskell and HTTP API. And the last one, the manual step, we write mapping between JavaScript and TypeScript languages. I think that will be fixed soon, just because only what we need is rewrite that step to the switch it from JavaScript to the TypeScript. So as you can see, most of the boilerplate code will be written for us automatically by our libraries, by our tools. And because the main part of our development of our project, it's a CAD itself, and user interface, it's only the instrument for debugging and analysis, we can focus on the CAD development. And if we broke something, we immediately know it from CI when continuous integration failed. The next approach, it's domain-specific languages for the test. The problem statement. As I already say, our CAD contain a very complex models of hardware processor units. And as a result, to check their function, we need to provide a lot of input data, check a lot of output data, and emulate a complex life cycle between the two input and output data. It's a very hard task because initialization of 2, 3, 5 functions to one process unit can consume a lot of source code, a lot of lines. And as a result, the tests, if we write it directly, as we usually do, that consume a lot of time for writing it, for reading it, and of course, maintaining it. Because if we change some essential data types, we need to fix all tests in all our projects which initialize or check them. And that is consume a lot of time. Also, when we write many code for our test, we usually can see the gap between the application domain and technical implementation details, because it's very hard to understand what really happens in your test if it's a long test. And as a result, in consequences, the tests tend to be not observable. So you cannot see in the test and in seconds understand what's happened and what's going wrong. One of the painful problems with that, when programmers try to reduce amount of line of code for each test by extract some parts to the global environment. And as a result, the only way to read and understand test is jump to the test in the test files and see different parts of its implementations. And the end of that problem, the tests tend to be not traceable and debuggable. What I mean? I mean that we see that some tests failed, and we need to spend a lot of time to really understand what happens, add some trace or debug code to understand what happened and why it happens. And usually, and sometimes, we cannot say that it is a bad test. Because if we have a complex unit, we cannot split it into another Monaro tests. But we don't have any options how to fix it on that level of representation. What is the approach to do it? It is using of application level domain-specific languages to test. And here you can see two examples on the right slide. First of one, it's a screenshot from Cucumber tutorial, which demonstrate behavioral-driven development, which focus in unit tests on how test logics actualizing, what's testing, when testing, and how testing. That is a not very simple to implement approach because requires to use a complex and hard software from my point of view. But our organization, the Ivan, he widely recommends that approach to design. What is the main benefits of use behavioral-driven development? That approach bring developers to write tests not only on the technical level, which is much easier to the programmers, but also to write it as a correct high-level test, which describes the behavior, the idea beyond this test, which allow to understand what happens. But in our project, it's not a very good approach because we don't find very well BDD framework for the Haskell programming languages, and we have very specific problems. And usually for different part of our software systems, we would like to design own domain-specific languages for writing tests. And you can see the example on the right slide on the black background. And here you can see the test, which in application domain term describe how synthesis method work with process units. And here you can see the assigning algorithm function to it. You can see the test data, what is specified for our test. Imitation of scheduling process when we make some decision how to perform computational process in target systems. You can see the access to the trace data for debugging process. If something going wrong, we can put it immediately to our test, and checking the main properties of our computational processes. What is that? I will speak on the next slide. What is the best benefits from usage domain-specific languages for testing tasks? That you can going up under the technical details to application domain, and that allow you to reduce amount of test code and amount of boilerplate code for your tests, and significantly simplify test development, test maintenance, and understanding. To compare the real domain-specific languages, like you can see in Cucumber, and embedded domain-specific languages. Embedded domain-specific languages usually is much simple to implement, because you don't need to design your parsers, lexer, and so on. You only need to describe logic of your languages inside your host programming language, like you can see here in Haskell. The same things can be easily done for any widespread high-level programming languages. For example, it can be Python, Ruby, Java, and so on. One of the interesting part of such approach that you can reuse element of test description to another test by describe fork of the test, different fork of the test, which is usually can reduce amount of source code reuse, but without breaking your test on the different parts, which increase the cost of working maintains such source code. Next, property testing and co-simulation. Here we take into account the two verification problem at once. First, it's a general problems of development tools, that the development tools have a very complex and heavy variety of input data, because we can write infinite number of application algorithms which should correctly translate it into the target systems. And as a result, we need to write a lot of test cases. And maybe you know, one of the, when BSD, free BSD operation system migrate from the GNU compiler to the CLang compiler due to the license reasons, they spend a lot of time to build the system, the kernel of operation system on new compiler. Why it happens? Because C has specification. CLang, it's not a new compiler when migration starts, but too many invariants embedded in our software. Too many corner cases can be found in software on the corner of optimization, parsers, abstract syntax tree representations, and many steps of our systems. So usually, to fully test such software, it's not enough to have only full source code coverage by the test. We need to test many of the different control sequences in our software, and writing tests for all of them, it's a very hard and very big task. For our project especially, because as I already say, our target processors building from processor units, and each of that processor units contains the two machines, the hardware implementation of that machines, the hardware implementation of processors, and the CAD model, which describe how to use it to performing application algorithms. And the only way to check, we need to check correctness of hardware implementation. We need to check CAD model implementations, their consistency for all possible variants of working with that. And usually our processor units support multiple functions. Any processor unit has own instruction set. Some of them allow to concurrent function executions, and some of them have finite internal resources. And all of that invariant should be checked during the testing process. And also, we should check the correctness of hardware consistency of hardware implementation and CAD models, because if they are inconsistent, we cannot generate the correct code. So what is the questions? How to compare, how to check consistency, and how to prepare enough amount of test cases to check our software, because we don't have infinite time to write tests. We need to write the software too. And here we have you can see our solution on this task. On the QR code, you can see the articles which describe in details how we do that, which is written by one of my students. First of all, to reduce amount of tests, we need to switch from the specification of correctness by input and output data to description the general properties of system behavioral. And the formal way to do that, the static way to verify general properties of the system, is designing is a certified programming. And here you can know some tools like IDRIS, COG, and another tools which allow us to formally check correctness, correspondence the software specification to some properties. Usually it's not widely spread because it's consumed a lot of time to formal proof, and that proofs significantly change when we change the software. So we cannot apply it in our project. But we know that we have another approach, very similar, but based on dynamic checking. It's a property-based testing, which widely spread in Haskell community, but also implemented for most popular programming languages. For example, I have experience with property-based testing with Golang and Python programming languages. What is the main idea? If we cannot prove some properties of the system in general case in static form, we can automatically generate any acceptable input data for our software and check some properties of the result. And here on the screen, you can see some examples. The first two, it's the classical examples of the properties. The first one, if we reverse list 2 times, we should receive the initial list, what we passed. And of course, you can see that in this case, that not prove the correctness of software, but that allow us to generate many test cases and prove these properties. Why it's not proof that anything is correct? Because if reverse list don't change the list, that properties will be true at all time. But of course, it's not the meaning of the reverse, but combination of some unit tests and property-based tests allow us to significantly increase amount test coverage and find a lot of bugs. The specific examples, the specific data and graphs you can see in the article, that by enabling property-based testing, we can increase test coverage for 20 or 30%, and how many control sequence we increase, we cannot measure because we don't have a tool for that in our development tools. In our case, what is the main problem about how to apply property-based testing in your project? The main problem is how to formulate, how to define general properties. And here we define the only 2 very simple properties of synthesis processes for our CAD. First of all, if we have some application algorithm, from these algorithms should be scheduled for executions. And of course, it's properties. Another properties is a co-simulation. What does that mean? That means if we generate the target systems, and you can see it on the stream, here we receive processor microarchitecture and algorithms, application algorithms. After that, we can simulate it in a functional way in our card without hardware, and in parallel branch, we can synthesize the target system. And after that, we can simulate the execution and compare them. If logical simulation and functional simulation have same results, we can say that mostly we don't have any significant issues in our code, in our models, in our synthesis method, and so on. And the last thing, what I want to say, here in this report, you can see some very complicated examples of the test. And the main problem when your test is not oblivious, when your tests require a lot of work and have complicated implementation, that you can test, your test can contain errors themselves. Your utilities for test can contain the errors. And the worst case, you can see on this brilliant comics. And when your test passed, but actually your test don't check anything. And that can happen in that approach. And here, the last term, the last idea, last point of the report, when you design so complex software test utility, you need to test themselves. And in our project, we do it a very simple way. We embedded special components in our systems, which design it to be bugly, to be this issue. And we create some flags which allow us to fail our system in a main common way that we have. And as a result, we not check our system on continuous examples. We also check our test environment on each CI interaction, which on each test execution. And that allow us to trust to our test environment and think, believe that if we make some issues, that we can find it faster than after a few months after the code was merged in the master branch. So the conclusion: automatization and processes, development processes, can partly replace and form development culture, which is a very important for the project when you work with many junior developers, because they need to receive fast feedback from the colleagues, from the mentors, and that allow to growing the expertise faster than without that. Second, merging documentation and unit test in a literate style can improve both of them, because we automatically check that documentation is up to date, and we also provide a good documentation to the software. If we test some simple function, We don't need to write unit tests because we can leave it only in documentation as interactive tests. Next, end-to-end static typing across different technologies can be implemented by code generation. It is hard to implement by yourself because it can require a lot of time, but the fast recognition of type issues can save a lot of time for debugging and for checking your software. And as a result, that approach is very good. And if your development stack allow you to do that, you should use that opportunity. If not, you can use standalone tools for serialization data. Next, application of domain-specific languages can significantly reduce complexity and number of line of code of your test and make them observable and workable. If your tests don't fit on the screen, I think you should use or see on that approach. Property-based testing can significantly increase test coverage for a complex algorithm. When we cannot write so many test cases and check all possible corner case for our algorithm, because we have too many such algorithms, or because we don't have enough time. But by automatic generation of input data for property-based testing, we can increase amount of tests from and the last item, last point is that if you don't use themselves, because wrong security feeling can bring you in a very bad situation. Thank you for attention, and I would like to answer your questions.
Thank you so much, Aleksandr. So for your talk, it was really very interesting and yeah, inspiring. Maybe one day I'll prepare a talk about our SD Cloud processes to share how we solve some things which we have in common between our project. Just one question. You said that you're using Haskell because of strong typing and ability to check a lot of things on the fly. So I know that languages like Rust and Go are also very picky at the compilation time about many different issues. So were any other reasons for taking the Haskell in background besides strong typing?
Before I answer, I want a little bit comment about Golang and Rust, because I've also have experience with that languages.
Sure.
Golang, it's not, how to say it, a good language to Haskell or Rust, because it's have static typing like a Java. It's a good, but it's not enough for complex algorithms. Second point, Golang has embedded lint tools. It is great because you don't need it. Not always useful. Then on V, but the Rust programming languages require manually work with memory. Not manually in C way, by borrow checker, which statically check your lifetime of your object. It consumes a lot of time to write it, but I really don't need it. So return to the Haskell. Another two questions. It is immutable programming languages. Our project contains a lot of models which should evaluate their state. And the problem from which part of software we change that state, it's a huge pain in the butt. And how to control over them, it's a very hard task. So we restrict mutable state and use only immutable. The second point, it is lazy programming languages that allow us not take into account many questions, what is really evaluated in computational, in synthesis process. As a result, we can forget about it and write all what we want. If we don't need it, we not really evaluate it. So we can have free from that. And the last one, it's a simple way to write concurrently software. The software written in a way without expensive. But I don't know why and how the compiler out of the box without any work from my side, which is great.
Okay, I see. Okay, thank you so much, Aleksandr, for the comments. Looks like we have some network interruptions. So there were some at the beginning of your talk and actually some happening now when you are answering the question. So I think that I would like to thank you for your talk. It was really very interesting. So I learned a lot of new things, especially about approaches on cross-language problems. That was really interesting and good. Thank you so much for this. Hopefully to see you someday again on our stage. So the video will be published in maybe a day or two on YouTube. So everybody will be able to just recheck our presentation. So thank you so much. I don't see any questions in the chat or any activity right now. So yeah, you can always reach Aleksandr directly. I think he showed his contacts. So thank you so much, Alex. Thank you, everybody, for joining.
I'm sorry, around.
Sorry?
Sorry, I miss your question.
Yeah, it was actually no second question because there are problems with the internet, looks like. So they happened sometimes during your presentation and a couple times maybe, and right now, so it's also happening. So I'm just saying that everybody can contact you directly or leave the comments on a YouTube video when we will publish it, so to get in touch with you. So great. Thank you so much for your talk. It was great and interesting. Have a nice evening and have a nice time of the day for others who joined from different countries and different places. Thank you and
good morning for you.
Yeah, thank you so much. Thank you. So thank you and see you soon, everybody, on the next sessions of Open Dais. Thank you. Bye.
Thank you. Goodbye.